As we move about in our daily lives, our physical experiences are typically predictable. We can assume that when we grab a cup of coffee and lift it off the counter, the force of our grip can do this job without us having to think too much about it. Of course, the unexpected can occur. But even then, our actions produce predictable results that can be described by using the same set of classical physical laws that Isaac Newton calculated centuries ago.
Newtonian physics is the body of physical law that emerged in the 1600s when Isaac Newton quantified what it means to describe the reality that we have access to. Objects have positions, they have speeds, and they're acted upon by forces. So in a construction site, when you see a construction ball swinging and smashing into things, Newtonian mechanics is the underlying mathematics that would allow us to calculate the trajectory of that ball, the impact that ball has when it smashes into the side of a building. So Newtonian physics is very much still with us. Sometimes people think about new ideas in science obliterating the past, making it obsolete, irrelevant. That's not the case. Even though we have refined Newton's ideas in the domain of quantum physics or in the domains of relativity too, in everyday situations that we human beings typically encounter, like a construction site or anything else you see when you walk around in everyday life, Newtonian physics is a spectacularly good approximation to describing what's actually going on. If you take any macroscopic situation, construction site, whatever, and we're able to shrink it down smaller and smaller and smaller until it became on a size on par with atoms, 10 to the minus 10 meters or so, then at those tiny scales, everything, every process is going to amplify and reveal the quantum nature of the universe. So for instance, you could have a wrecking ball heading toward a wall that it's trying to smash through. And in the quantum version of that, the wrecking ball could actually pass right through that wall without smashing it at all. It could tunnel right through it. Quantum tunneling. And it could quantum tunnel back. Something that would be utterly absurd in any ordinary situation. But in the microscopic domain, these kind of weird things would be part and parcel of what happened all the time.
What's happening at that subatomic level, where atoms are only 10 to the minus 10 meters or so? The level of quantum mechanics.
Quantum mechanics is the body of physical law developed in the early part of the 20th century by a single generation of physicists in order to have an accurate description of how particles behave in the microscopic realm.
If you thought an atom looked like this, you would be wrong. Electrons don't orbit the nucleus like planets zipping around the sun.
You would have thought, if you were a physicist at the time and didn't know about quantum mechanics, that electrons should behave like little baseballs, right? They're just little particles. We have the laws that govern the big versions, and those laws should be the same laws that govern the small ones. The data showed that that was not true. The data showed that if you use Newton's ideas in the realm of particles, you'll get wrong predictions.
If we were to apply Newton's laws to the atomic world, the electrons would collide into the nucleus and self-destruct every fraction of a second. Instead, electrons behave more like vibrations, each with its own frequency.
Now the laws of quantum physics come into the story because you've got electrons that are in quantum clouds surrounding the nucleus of the atoms that are making up that particular object. And to understand those structures and those properties, you need new equations that Isaac Newton didn't know about.
In 1894, physicist Max Planck was hired by the German Bureau of Standards to help design a better light bulb. Planck investigated the qualities of heat, energy, and light in a series of experiments. As a light bulb filament heats, its color changes from red to yellow to white. But why doesn't the light get bluer at the higher end of the spectrum when more energy is applied? Planck made a groundbreaking assumption that energy is not delivered in a continuous wave, but in packets, or quanta. And these quanta are uniquely and mathematically proportional to a given frequency. This means that certain frequencies only hold certain amounts of energy. The new understanding of packets, based on Planck's observation, described a new physics. Planck received a Nobel Prize, and quantum mechanics was born. In 1905, a young patent clerk named Albert Einstein published 4 papers that upended the field of physics. Einstein may be best known for his theory of relativity, but it was his paper on the quantum mechanics behind the photoelectric effect that eventually earned him his Nobel Prize. The photoelectric effect happens when light is shown on a metal surface, and electrons are given enough energy to escape. So, using Planck's formula, Einstein proposed that only certain wavelengths can carry enough energy to release electrons, regardless of how intense the light is. Therefore, light energy is emitted in wave packets, or photons. But can a single photon of light also be a wave? The double-slit science experiment shows us how.
In one single experiment, the double-slit experiment, you can see the heart of quantum mechanics laid bare. And the experiment begins like this. We have a barrier with 2 openings. It's called the double slit. And we begin by firing large objects, pellets or BBs, at this barrier. And as you would expect, those BBs that go through the right slit will land in a band on the right aligned with it. Those BBs that go through the left opening land in a band aligned with it on the left. Now we're going to make one adjustment to this experiment. We're going to take those projectiles, those little pellets or BBs, and we're going to dial down their size, making them smaller and smaller and smaller until they are as tiny as little particles, electrons. And we're going to do exactly the same experiment. Now you would think that if we fire these little electrons, more or less we should get the same result. Those electrons that go through the right slit land on the right in that band. Those that go through the left land in that band on the left side. But the thing is, if you do this experiment, this is not what happens. Instead, if you actually do this experiment, what you find is data that looks like this. Not just 2 bands aligned with the 2 openings. Instead, you get a whole series of bands. This is the heart of a revolution. And the key comes from another area of science called waves, right? If you are by a pond and you have 2 pebbles and you throw one pebble into the pond, you know what will happen. Pebble hits the water and it sends out these concentric ripples that spread outward. If you throw the other pebble in, you know what will happen. The exact same thing. Concentric ripples will be sent outwards. But if you are a careful observer and you throw both of these pebbles in and you look at what happens when the waves crisscross, you'll find something interesting. There are locations where the peak of both of the waves combine to make the water a little bit higher. There are other locations where the trough of each wave cross to make the depth of the water a little lower. But there are other locations where the peak of one wave crosses the trough of another, canceling each other out. At those locations, the water is not moving at all. The waves have interfered and canceled each other out. Imagine you throw in these pebbles, one on the right side, we throw in another one on the left, and where the waves are crisscrossing, there are locations where the waves are canceling each other out, and you can begin to see those coming into view here, the dark areas. Exactly the same kind of data that emerged in the little experiment where I was firing electrons at the two openings. So if you go back to the double slit experiment, the idea is now think of the electron as a wave. Like a water wave, it can crisscross on its way to the back screen. Locations where the wave cancels each other out, the dark regions are locations where you will find very few particles. Bright regions are where you will find the electron many times. So this is the core of the new idea. It's telling us that the world consists of waves of probabilities. You know, if scientists hadn't developed quantum theory, you could still imagine that very creative, smart, industrious engineers and thinkers of all sorts would still have learned how to manipulate the world on microscopic scales. They might not understand really the fundamental underpinnings, but through spectacularly inventive trial and error, you can envision that they would have developed much of the technology that we enjoy in everyday life. Cell phones and computers and all sorts of objects which rely on integrated circuits that we understand well because we have grasped the quantum laws. But what we'd be missing in a real vital way is the deep theoretical underpinnings of everything we see in the world around us. And that would be a huge loss.
Einstein and Planck may have opened the door, but it took another generation of physicists to dive deeper into the quantum world.
The uncertainty principle of Heisenberg was really a sharp turning point in the historical development of quantum mechanics.
Quantum mechanics revolutionized physics, but not without controversy. Find out who wins, who loses, and why reality might be stranger than you ever thought possible.